Hi, y'all. Back for another round of physics, I see. And just a little byline, again, following along some discussion in class, I said, oh, yeah, that's a really interesting point about Young's modulus. So this is a video just dealing with springs. Give you an idea. Of course, we're probably not going to pursue this very much further, but I wanted to at least give you some sort of conceptualization of what's going on with Young's modulus and why it's so important. So here we go. Let me start off with this. We're going to talk about springs. And the more important question, okay, so we're going to actually have a discussion about springs first. Springs. And the question I would like to know is, how do springs behave when they're in parallel and when they're in series? How do they actually behave? Now, this behavior will actually become important later on in your careers. Well, if you're dealing material science, of course, but even when you start dealing with things like resistors, capacitors, inductors. These will also follow some similar rules, and I'm sure there's other objects out there that follow these rules as well. These are just the ones that immediately come to mind. So let's get at it. Here's the situation. Say I have a box, okay, and I'm suspending it with two springs. Okay, so I have a box of mass m, and I'm suspending it by two springs, each of spring constant k, and we'll say that the stretch length of these springs is delta L. Okay. Okay. Now, the question, first of all, is, say instead of doing two springs, I would like to do it with a single spring. I would like to suspend the same mass with only one spring, which I'll call it K effective, or I'll put equivalent, so I'll put K EQ, and say I also want to have it stretch a distance of delta L. And the question is, how does KEQ, the equivalent spring constant, compare to the individual spring constants? Okay. And here's how we're going to do it. So how I would like to do it is, why don't we go for, I don't know, let's go for energy. Okay. Since the box stays at the same height above the ground, call it like this, so there must be some sort of potential energy stored in the springs. And the route I'm going to go is I'm going to say that, hey, wait a minute, the energy in the springs should be the same. In other words, for situation 1 or situation 2, the energy in the springs should be the same. Okay? Well, let's go over here. Let's take a look. This is just 2 times 1/2 k delta L squared. And that should be equal to 1/2 k EQ delta L squared. Right? They're stretched the same amount. I want them to store the same exact amount of energy. How do the spring constants compare? You say, oh, goody, goody, I got this, Greg. The 1/2s and the delta L's cancel out. That's all nice and dandy. And we find out that, hey, wait a minute, 2k, twice the individual spring constants, it must be my value of the equivalent spring. Okay. And in fact, you can do this pretty much more generally. You could have different spring constants, k1 and k2. Of course, you'd have to figure out what does that mean about the stretch distances, but it's a general idea that holds. And I'll write it like this. The sum of the individual spring constants, ki, will equal KEQ when in parallel. Okay. So this arrangement is what we would call a parallel arrangement of springs. Okay. A different way to say it, I guess, is, if you're curious, how do I define parallel? You could say that parallel springs touch the same two objects. Okay, so I'll say parallel, say they connect same two objects. So there we go. We've got some idea about, hey, when our springs are in parallel, so I'll say KEQ parallel, this is simply equal to the summation of the individual spring constants, Ki. Okay. Rock and roll. Well, the other question is, you don't necessarily have to have springs in parallel. Let's go at a different situation here where I have two springs in what we call series. I'll call it K and K again. And they're hanging a box, M. Now you notice here that because the first spring doesn't connect the same two objects, right? The first spring connects the ceiling to spring 2, and the second spring connects to spring 1 and the box. So it's not the same object. These are what we call in series. A different way to say it is, in order to get to the second one, you have to go through the first. Okay? So that might be a different way of defining it. And we'll say that the first spring, of course, stretches a distance of, we'll say, delta L. And then the second spring stretches a distance of, again, delta L. And we'll play the same song and dance. I wish to replace this with a single spring, okay, of KEQ. And of course, the stretch length of this spring is 2 delta L, so that it hangs at the same height. So let's go at it. Again, I need these two to store the same amount of energy. I guess in thinking about this more, why do I insist on this? What we want to do is, hey, is there a way for us to conceptualize this system of springs, which I'm circling here? Is there a way for me to conceptualize this system as springs as being a single spring? And so that being the case, I have to insist that all of the physical ideas are the same. In other words, I have to insist that they both have the same stretch distance. And I have to insist that they both have the same energy. If I do this, then conceptually, it doesn't matter if I look at individual springs or if I look at a single spring or multiple springs. Okay? From the modeling standpoint, it'll be the same situation. That's a better way to think about why do I set this restriction in the first place. So let's go ahead. Here you have something that says 2 times 1/2 K delta L squared. And on the other side, you have the 1/2 KEQ, keeping in mind that this must be 2 delta L squared. There we go. Oh, goody, goody. The 1/2s and the delta L's cancel again. And we end up with something that says, okay, well, this is 2K must be equal to 4 KEQ. Or the individual springs divided by 2 must be equal to KEQ. Pretty cool. And the more general situation would be something akin to this. And how we would actually get that. Now, this one, it doesn't look quite the same. But what I'll do is I'll flip it. Say, why do you flip it? But here's what the actual expression should look like. So the summation on I of 1 divided by Ki equals 1 divided by KEQ. Now, if you want, we could go in and actually figure out this from an individual spring basis. But what we see is that if the springs are exactly the same, so if they're all the same spring KIs, then you would just get the number of springs, KI, divided by the number of springs. If they're all the same, this is what this expression would boil down to, would be equal to KEQ. So this is the more general, particularly important if your springs are different spring constants. Okay. So I'll go ahead. Let's go ahead and move this one. We'll put it up here as well. And so now we have our two expressions. One is for parallel. The other one is in series. There we go. Okay, well, let's get some idea on why this is kind of cool for material properties. So let's imagine for a second, let's go ahead and we'll draw a box. I'm not particularly good at boxes, but we'll do this. Okay. So what I'm going to do, there's a box. And what I'm going to do is let's pretend that we slice it. We're going to slice a face off. In other words, let's go ahead and just consider this top layer for a second. So let's say I have a box of uniform material, so some atom, form material. And what I am after is, how can we get an idea about the effective spring constant of this block? So I want K effective of block. Or in other words, what's the spring? If I wanted to model this as a spring, what should I model it as? What's the spring constant of that? Now here comes the conceptually tricky part. Okay, let's go ahead and if we consider an atom, so consider an atom that's in this block, and rather than considering it to be a sphere, right, a sphere of some radius r. Rather, what I would like to do is let's go ahead and model it instead as a square box. So we'll go ahead and put a square box in here. And I'm sorry, I can't draw in 3D for a sphere. So we'll model it as a square box of a length d. So rather than thinking of atoms as spheres for this situation, we're going to think about it as square boxes of length d, where the box perfectly encompasses the sphere. Do you have to do this? No. This just makes it easier for our conceptual purposes right now. So here's the question I have for you. In terms of d, how many atoms will be in this top layer that I've specified here? How many atoms are going to be in there? And let's say that the top layer, has an area of A. So if the top layer has an area of A, and I'm approximating my atoms as being cubes of side length d, how many atoms are actually in this top layer? You got it? Good. So you say, I got this, Greg. You can think of this top layer as being divided up into a bunch of different cubes, right? Checkerboard pattern. Okay, so each one of these. So what I can think of is the number of atoms in that top layer is simply the area of the top layer divided by d squared. Good. Excellent, excellent, excellent. So here's the next question I have for you. So instead of thinking about that top layer, let me ask you this. Let me take a single column of atoms. So in other words, what I'm going to do is I'm going to take this single column. Okay, so you have another one, another one, another one, et cetera, et cetera. And if the total length of this column is L, can you find out how many atoms long it is? Good. You got it. Okay, so N equals big L divided by D. So if I want to know how many atoms are in the top layer, I take the cross-sectional area divided by D squared. If I want to know how many are in a column, I take the length of my object and divide by D. Perfect. Now here comes the next one, the next kicker. Let's approximate each of these individual atoms. So these cubes that we have, we are going to approximate that they are connected by some interatomic spring. Okay. So what keeps these blocks glued together, we'll call it K, and we'll call it the interatomic spring constant. What this means, we're going to model the atoms as if they were connected by springs. Now, that might bug you a little bit. And I'll remind you two things just to try to calm your nerves. Okay. The first one is this. Okay. Please remember that the potential energy given by a spring is 1/2, call it kx squared. So do that. Okay. So that's the first thing. And the second thing I'm going to remind you of is that at one point you had a homework problem. In fact, we just talked about it for the last video, where you were asked to plot the potential energy function of two atoms connected. Now, I don't remember exactly. I'll leave it to you to remember, or I'll pop it up and say, okay, here's the potential energy function. But here's the key. When we plotted it in the last video, you notice that it went down, it kind of loops up, and then it kind of asymptotically approaches 0. Okay. And what I want you to focus on, or what I'll actually talk about, is right down here, right at the base. Okay. If I blind myself, if I just look at, say, this area, really close to the base, the minima, what we can do is, you notice that this almost looks like it's quadratic. Now, over here at the tail, that's a bit off, so maybe I got to be closer. Maybe I need to blind myself and just look at these two areas. But you notice that right in there, this curve no longer looks like, if I ignore everything outside the yellow lines, this curve almost looks quadratic in nature. In other words, some kind of parabola. What does this mean? This means that close to equilibrium, remember that this was the equilibrium distance, REQ. So close to equilibrium, the potential energy U of R is approximately quadratic. In other words, we can approximate this goofy interatomic spring potential, interatomic potential energy as simply being like a spring between two objects. Okay. That's just a really cool kind of approximation that we make. So long as you don't stretch these two atoms too far apart, if you remain in this regime that looks fairly quadratic, then we can treat it almost like a spring. What's actually physically going on there, of course, it's, say, for example, you have hydrogen. If you have two hydrogen nuclei, what's actually going on is some sort of covalent bonding, some sharing of the electrons. Okay. That kind of acts like a spring in some sense, so long as they're close together. Okay. If they're too far apart from each other, all bets are off. So that's just a little chemistry, just to kind of make you feel a little bit more confident on what's going on here. Okay. So what we're going to do next, let's go ahead and get rid of this. So here's where the magic happens now. Okay. If you notice, M represents the number of springs in parallel. It represents the number of springs that are in parallel on this top layer. Okay. So what I'll say is the effective spring constant, or the equivalent spring constant of a layer parallel, is equal to M times the interatomic spring constant. the number of springs in the layer or in parallel, which we found previously, times the spring constant between them, between the atoms. Okay. Of course, we can substitute in, we have an expression for m, and so we could write this as A divided by d squared times the spring constant K, the interatomic spring constant. But wait, there's more. We have n layers of springs, right? We counted up the number of layers that the object was, how many stacked layers it was. So we can keep going. So what we now have is that if we have n layers, okay, so n springs in series, so you can think of, let's take each layer and model it as a spring that has an effective spring constant of a layer. Okay, so now we're modeling it like this. Rather than a physical three-dimensional object, we're modeling it as a single spring that's K layer, and a second one that's K layer, and a third one that's K layer, dot, 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 dot. Okay, a bunch of springs in series. And we can see from up here, right here, that what ends up happening is that we have n springs, each one of K layer, and that must equal 1 over K equivalent. I'll say the equivalent spring for the entire block. Now we have this. Let's flip these two equations. We have K, I'll just put it as the entire block, is equal to the spring constant of a layer divided by n. And then we'll take this equation and substitute in for the layer. So we get the area over d squared times the interatomic spring constant K. And we also have an expression for n right up here, which we'll also substitute in. It's like magic. That would be L over D. Oh, goody, goody. You get a little bit of cancellation. That squared goes away, that squared goes away. And we get something that tells us the spring constant of the entire block is equal to the area of the block times the interatomic spring constant, the size of the atom, or a different way of saying it is the separation distance between atoms, and the length of the block. Yeah, yay, nay. Are you excited yet? Maybe. Okay, I'll put these over here. Sorry, I'm running out of places to put this stuff. I guess, oh no, I guess I'll just leave it there. Maybe move it up slightly. No, you're not excited yet? How are you not excited about this stuff? So here's one more thing that I'll give to you then. Let me rewrite this. So I'll say K of the block is equal to a interatomic spring constant d times the length of the object. Now, one of the cool things about this, notice that I'm starting to relate macroscopic quantities to microscopic quantities. I'm relating physical distances that I can measure with a ruler, area, the length, maybe even the spring constant of the block, the overall spring constant, to microscopic properties, the interatomic spring constant and the distance between the atoms, which is a really cool thing. In fact, if I go ahead and scoot stuff over, I get something that says L over A times K block equals the interatomic spring constant divided by D. So if I could measure these three things, then I have an idea about the ratio. Okay, so there's one more trick in the book that really, where stuff really starts getting exciting. So we'll go ahead and throw that in right now. And it's called Young's modulus, capital Y. Now, this is a definition. It is defined as the strain over the shear, I believe is what it was. Call this delta L over L. Okay, so sometimes this is called the strain, if I'm not mistaken. And this is called the shear. Said, I'm sure I'll correct myself later if I got that wrong. Now here's the issue. What do you do here? Well, let's say we take a 10 kilogram mass, which I've already drawn in here, and you hang it from this bar. Okay. Now you already know the area of the bar, you know the length of the bar. And when you hang the 10 kilogram mass, you now can say something about the force acting on the bar and the change in length. Okay, so we have everything on this side if we want to do it experimentally. That's how you get Young's modulus of the material, actually. You take a well-defined object, you hang a well-defined mass, you can then say something about the Young's modulus. I'm going to take this definition, though, and I'm going to rearrange it a little bit. So what I'm going to do, let's go ahead and get at this. If I take Young's modulus, and I'll rewrite this without the compound fractions, get L over delta L, and I'm going to move everything over to the other side. Okay. So in other words, I'm going to write it like this. Excuse me. YA over L, and I'll put a delta L here, equals force. And this should look awfully familiar. Okay. And in fact, you can get an idea about this. If I take my 10 kilogram mass as the system, I've got a gravitational force down, which I'll call F of G. And I've got a force upwards, which I'll call I'll just call it F of block. So if I apply Newton's second law, you find out that, hey, the force that the block exerts is equal to the gravitational force. The applied force, if you will. So, hey, wait a minute. I could use this as the force of the block. Right? The force that the block exerts on the 10 kilogram mass. Now, if I look at this, this looks kind of familiar, or at least hopefully it should. The force is equal to a change in distance times some value. This all looks an awful lot like Hooke's law, right? If this were the spring constant and this is the change in distance, that would be Hooke's law. So what I'm trying to point out to you is, hey, this must be an alternative way of expressing the spring constant of a material. If I have Young's modulus of the material, if I have the cross-sectional area of my object and the length, I can say what the effective spring constant will be. Right? How much will this object stretch when I hang a mass off of it? Which is wicked awesome. It's really cool. Say, but wait, there's more. You say, oh, I can't take any more. Or yes, you can. There's more. Wait a minute. There's so much more. Well, just a little bit more, not a lot. You're saying it's a 30-minute video, Greg. I don't need any more. Oh, yes, you do. So I'll put Young's modulus times A over L. Excuse me, that's, yeah, okay. This is also equal to K, I'll say effective. Excuse me. Call this K block. So we'll go for the last piece. Notice that I have an expression, the spring constant of the block, that came from just simply counting springs in series and parallel. I also have one from the definition of Young's modulus. I'm going to set those two equal to each other. So I get something that says the area times the interatomic spring constant divided by L times the interatomic distance. That must be equal to Young's modulus times the cross-sectional area divided by L. Cool. You see that? Oh, goody, goody. cross-sectional areas cancel out, the lengths cancel out, and what do I get? I get that Young's modulus is the ratio of the interatomic spring constant divided by the interatomic distance. Okay. Whoa, wicked awesome. But if you have the molar mass and the density of the material, you can actually find out the spacing of the atoms. So then you can use Young's modulus, the molar mass, and the density of the material to get the spacing, and that, voila, you can get the interatomic spring stiffness. My recollection serves me correctly, it's not very big. It's something like, I think for copper, it's somewhere around 10 newtons per meter, which is a fairly weak spring. You don't think of copper being that weak, but the issue is that you have so many copper atoms in a cross-sectional area that even though an individual spring might be really weak, the summation of them is huge, just absolutely huge. Okay. So now that we've had a discussion about Young's modulus, let's go ahead and do an example where we find how stiff the spring is between the two atoms. So I've done a little bit of looking up, some searching, and we'll do this for copper. So copper, and what we need for this, as hinted, was we need to have some sort of atomic mass, or the molar mass, so I'll call that capital M. And that's equal to, for copper, that's equal to 63.5, and this would be grams per mole. Along with that, we're going to need the density, so we better put that in there. The density. And this, the density of copper is, let's see here, I got it here. 8.96 grams per cubic centimeter, cm cubed. Okay. Also, what we're going to need is Avogadro's number. Okay. And truth be told, I always forget this one. It's 10 to the 23rd. Okay, there we go. So 6.02 times 10 to the 23rd, and this would be atoms per mole. Okay, that one comes from chemistry. And last but not least, we'd actually have to go up and look up Young's modulus for copper. Oops, copper. And this turns out to be some astronomical unit, 117 times 10 to the 9th newtons per meter squared. Okay. 117 gigapascals. Okay, so this is known as a pascal. Sometimes you'll see this as PA, but what it is it's a newton per meter squared. So these four numbers are enough for us to actually figure out how stiff the springs are between atoms of copper. Incidentally, just to remind you again, how would you actually get this experimentally? Well, you'd take a copper rod or some object. You would measure the cross-sectional area. You would measure the length, L. You take some mass, say 10 kilograms, and hang it. 10 kilograms, hang it, and measure the delta L. And from that should be sufficient for you to actually figure out what the Young's modulus is. What you do is you take the applied force divided by the cross-sectional area, and you divide it by the change in length over the total length of the object. And in fact, we could do this in the lab if we really wanted to. You just take a copper wire and just start hanging masses and measure the distance or the change in length. So that's how we actually get this number. So how do we actually use this? Let's go ahead and get rid of this. How do we actually use this to find the spring constant? Well, where I'm going to start, pick your flavor. I think I'll start with the density. And for sake of units, what I'm going to do is I'm actually going to start looking at the 1 over the density rho. Okay. What this is equal to is, I'll put cubic centimeters up here, cubic centimeters divided by 8.96 0.96 grams. Okay. And what we're going to do is we're just going to simply figure out how many centimeters per atom. So what I need to do is I need to actually change grams into atoms. And if I can do that, then I've got it. I've got the cubic volume of a single atom. So how do we go ahead and do this? Well, first, what I'm going to do is I'm going to multiply by the molar mass. So if I multiply by, let's see, I put the grams on the top, so I have 63.5 grams per mole. Okay. That's what the molar mass is. And excuse me, maybe I shouldn't have this equal sign in here anymore. So I'll go ahead and get rid of this. Okay. So now I see, oh goody goody, the grams cancel out. Certainly that's okay. So now I've gotten rid of my grams. And now I need to figure out some way of relating how many moles, how many atoms are in a mole. Well, that's just simply Avogadro's number right here. Okay. So let's see here. I want the moles to cancel out, so I better put moles on the top. So I'll put 1 mole up here. And I'll have Avogadro's number, 6.02 times 10 to the 23rd. And I'll put atoms. So maybe I'm going to make that line a little longer. There we go. And so at the end of the day, oh goody goody, I get another cancellation. And so at the end of the day, what I have found now is the volume per atom of copper. Okay. So I'll say the volume, put the volume of a copper atom is equal to, I guess I'll do it like this, 1 over rho, right? Run over the density. And I multiplied by my molar mass, m, and I divided by Avogadro's number. That's the volume of a single copper atom. This would be the more general expression for what we're doing up here. Now, if I recall, I'm treating each copper atom as if it were a square cube of side length d. What that means is that the volume is equivalent, you could also set this equal to d cubed. And so if I take the cube root of this rigmarole, so first of all, maybe I should actually, let's go ahead and calculate it. So the rigmarole, I get, oops, excuse me. I get the volume of the copper atom is equal to, get the volume is equal to, oh, where'd my cursor go? There it is. I got 1.177 times 10 to the negative 23rd. This would be in cm cubic centimeters, because that was in cubic centimeters. If I take the cubed root of that, so I raise that to the 1/3. I get something like d, the distance between the atoms, is something like 2.27 times 10 to the negative 8th centimeters. Or if I prefer, and this is probably preferable, let's convert that into meters. So centimeters, if I just wanted in meters, this would be to the negative 10th. Or if you recall correctly, this is sometimes called an angstrom. Okay. So that's roughly the spacing between the individual atoms right here. So let's go ahead, we'll take that and let's move this result over to the other side. There we go. So using these first 3 values, I'm able to find the interatomic spring spacing. Well, we are almost home free now. I said, hey, we can get an idea about the spring constant between the copper atoms. So we took some chemistry stuff And now let's go ahead and use our idea about Young's modulus. Previously, we related Young's modulus. We said, well, hey, this is just simply the spring constant, K, divided by the interatomic spring atomic distance. So the interatomic spring constant divided by the interatomic distance. So we get that the spring constant between copper atoms is something on the order of Young's modulus times d. Well, we have a value for Young's modulus, 117 times 10 to the 9th, which seems like a wicked big number. But then we realize that the spring spacing is pretty stinking small, 2.27 times 10 to the negative 10th. So let's go ahead and run those numbers. If I run those, 7 times 10 to the 9th, enter. I indeed, at least I got something, hopefully your calculator gets the same, I got something like 26.6 newtons per meter. Pretty cool, huh? So that's just an example of how you can actually mix a little bit of chemistry, some stuff that you find on the periodic table, and some little engineering, this Young's modulus. You can combine those two and get this microscopic quantity, how stiff the springs are between the individual atoms. I gotta say, that's pretty cool. In any case, that's all I have for now. I encourage you, try that again. You don't have to use copper. You could do it for lead. You could do it for, say, some other material, say diamond, for example. You can do that all over the place. You just have to look up the Young's modulus and get the density and the molar mass as well. So, hey, I think that's it for right now. I thank you for your attention. I'll see you next time.